How are you, my friends? This is a continuation of the Algebra course, lecture 38. This is the one before the last lecture. This is about complex zeros of polynomial functions. And we look at the Conjugate Zeros Theorem also. So these are the ideas and the objectives of this lecture. We will see all of them. The fundamental theorem of algebra says that every polynomial p of x written in this form with complex coefficients has at least one complex zero. So they should be at least 1, 0. The word zero here means if you replace this number in the function, you will get 0. Also, this theorem applies to polynomials with real coefficients. Now, using the fundamental theorem of algebra in the previous slide, we can see that p of x can be written in this form: a, x minus c1, x minus c2, x minus c3, etc., until x minus cn, where these numbers c1, c2, c3 are the zeros. So we can multiply all of them to get the function, and we have to put a here at the beginning. This is the leading coefficient. It can be 1, it can be positive or negative or fraction. Let's look at example 1. The first one is easy, I said here, and the second one is not easy. This one, find the complete factorization of this function, x cubed minus 3x squared plus x minus 3. So directly here we can factor. So we factor if we can. Like this one, we can use grouping. Take x squared common, this is x minus 3, plus put in the bracket x minus 3. Take x minus 3 common factor, and we have x squared plus 1, which is factored as x plus I, x minus I. So this is the complete factorization. Now, second one, why it's not easy? Simply because we cannot factor. So if we cannot factor, I taught you this method here. If you cannot factor, use the rational zeros theorem or P over Q. So P, the factor from the constant term 4. Q is the factor for the leading coefficient 1. Find the possible rational zeros P over Q, and then try synthetic division. If you pick up minus 2 from there, you see the remainder is 0. You know how to do synthetic division. Then we stop here because we have a cube, and then we found 1, 0, minus 2. All right, so why we stop? Since 2 zeros are left, because I can take the quotient here, x squared minus 2x plus 2, and then find the zeros either by factoring or by quadratic formula. In this case, I cannot factor x squared minus 2x plus 2, so I use the quadratic formula, which gives 1 plus or minus I. Now I know if c is a 0, then x minus c is a factor. We know that. Then I can write x minus, this is the first 0 minus 2, x minus the second 0, 1 plus I, x minus the second one, 1 minus I. Then this is the complete factorization. Now the number of zeros theorem, a polynomial here, function of degree n has at most n distinct zeros. So the maximum number of distinct means different zeros. The maximum we can have is the same as the degree. So if we look at this simple example here, x plus 3, x minus 7, x plus 1, x plus 4i, x minus 4i, we see that the degree here is 6, and these are the zeros. So there are 6 zeros because all of them are distinct or different, 4 real and 2 complex. Now some zeros are repeated. We have mentioned this before. C is a zero of multiplicity k, which means this 0 is repeated k times. So if you look at this example, p of x, polynomial function, x minus 1 cubed x plus 2 squared, x plus 3 all to the power 5. We see the degree here is 10 because x power 5, power 2, power 3 if you add them. So this function has the following zeros. 1 is a 0 of multiplicity 3, repeated 3 times, minus 2 of multiplicity 2, and then minus 3 of multiplicity 5. Just to mention that if you add the multiplicities, 5, 2, and 3, it will give you the degree, always. Now, some examples here, simple examples. I put degree 1, this is a polynomial as an example, degree 2, another polynomial, degree 3, another polynomial, x cubed plus x, degree 4, I put x power 4 plus 18, x squared plus 81. You can factor it easily. And then degree 5, there is x power 5 minus 2, x power 4 plus x cubed. Just read these examples. These are the zeros with their multiplicities, and this is the number of zeros. The number of zeros is the same as the degree, total number of zeros. Now, some may be real, some may be complex, some may be repeated. New example, list all the zeros and their multiplicities. So here we have a function p, 1 minus x, x plus 7 squared, x squared minus 9, all to the power 4. Find the degree and describe the behavior. This one is halfway factored. We have to factor more here. You see x squared minus 9. That's the difference between 2 squared. So I can write x minus 3, x plus 3, each one to the power 4. See, this is like x times y all to the power 4 will be x to the power 4 times y to the power 4. So the zeros are here 1, multiplicity 1, because the power here is 1. The 0 is minus 7 repeated 2 times, 3 repeated 4 times, minus 3 repeated 4 times. Now the degree is 11 because this is here power 1, power 2, power 4, power 4. When you add all the multiplicities, you get 11. The leading coefficient here is minus 1. I can take a common factor here to make it x minus 1. So all these coefficients of the x's are positive, and there is a minus 1 there. So behavior is similar to the minus x cubed, up to the left and then down to the right. Find a polynomial q of x of degree 4 with the zeros 0 and minus 2 of multiplicity 3. So we have the zeros here. We have to build up the function. So easily we can start with q of x. A, x minus c1, that's the first 0. The second 0, x minus c2, all cubed, because it said in the question, multiplicity 3. So we have a x minus 0, x minus minus 2 cubed. You get this function here. And then you expand x plus 2 all cubed by the formula. You multiply by x. Now we see in the question here, no given conditions for q of x. If you look at the question here, there is no condition on q of x. So directly we say a is equal to 1. So this is the function. Okay, that's q of x. Conjugate zeros theorem. This is very important theorem. If we have a function polynomial that has a real coefficients, remember this is an important condition. If we have a function with real coefficients and a plus bi is 0 of this function, then we can conclude that the conjugate a minus bi is also another 0. That's one example here. We have 1, 0, minus 2, 5i, and minus 5i. Let's see another new nice example. Find all the zeros of this polynomial function of degree 4, given that 2i is a 0. So we look at, first, we look at the coefficients, 2, minus 1, 7, minus 4, minus 4. These are the coefficients. You see, the coefficients are real. So easily now, since we have 2i given as a 0, directly we can say also minus 2i is another 0. So I take synthetic division. I take all the coefficients, 2 minus 1, 7 minus 4 minus 4. I have to go slowly here. And then I divide by 2i. Why 2i? It is given a 0. So I know that the remainder should be 0. Then 2 comes down, multiply 2 times 2i, 4i. When you add here, this is real and imaginary. We cannot add them. Just put them like this. Continue multiply with 2i until you get the remainder 0. Then we divide by the conjugate minus 2i. Also, we should get the remainder 0. So we stop here. Why we stop? 2 zeros are left. So we have the quotient 2x squared minus x minus 1. We factor it. So we get x equals 1, x equals minus half. So these are all the zeros. If you cannot factor here, you can use quadratic formula. Another example, if 3i is a 0 of this function, very similar to the previous one, but here we need to find the number of x-intercepts. This is also degree 4, so we know there are 4 zeros. They can be real, complex, repeated, etc. So 3i is a 0. Directly I check the real coefficients. 1, 1, 7, 9, minus 18. Yes, real. So directly I can say 3i is a 0, so I divide 1179 minus 18. I divide by 3i, and the remainder should be 0. Then I divide by minus 3i, which is the conjugate, and also the remainder should be 0. You can check, guys, you can check all these numbers and do it by hand to understand it better. Then x squared plus x minus 2, factor it, I get 2 zeros there, 1 and minus 2. So these are the real zeros. So the question says, find the number of x-intercepts, which is the number of real zeros, which is 2 numbers there. So the answer is 2. Another, find a polynomial p of x of lowest degree with real coefficients with zeros I, 2, and minus 2, and p of 3 is equal to 25. See, that is a condition on the polynomial function here. See, that will decide what is a. So we have I, 2, and minus 2. So what will be the lowest degree here? I think you can answer it. The lowest degree will be 4. So we have given real coefficients, and we know, if c is a 0, directly we can say x minus c is a factor. So we have to put a, x minus c1, x minus c2, x minus c3, x minus c4. Put all the zeros I, and there is also minus I, and there is 2 and minus 2. Now, when you multiply the first 2 brackets here, you can use the sum of 2 squares because we have an I there. X minus 2, x plus 2, you can multiply by difference of 2 squares. So the last 2 factors here, we get x squared minus 4. Here we get x squared plus 1. Now we need to find a. So this is what we get from last slide. And we have given condition p of 3 is equal to 25. So x will be 3 and y will be 25. Just put here 25 for y, 3 for x. See, this is 3 squared, this is 3 squared, so a will be half. So this is the function, p of x half, x power 4 minus 3x squared minus 4. When you multiply these two, and this is the function p. Now example 7 says, find a polynomial r of x of least degree with real coefficients that has zeros, I, and 1 plus I, and constant term 12. So there is a condition here on the function, constant term is equal to 12. And then we have 2 zeros there, 1 and 1 plus I. So we have the real coefficients. That means the conjugate of the I is minus I. The conjugate of 1 plus I is 1 minus I. These are also zeros. So I can write R of x, the function, x minus C1, x minus C2, x minus C3, x minus C4. There are 4 zeros there. Now this is easy in the complex. This is also easy, but we have to rearrange it. So I can make here some rearrangement, x minus 1, see here x minus 1, and this becomes minus and this becomes plus. On the next slide we see Now, after I rearrange it, I write it in a smart way here. You see x minus 1, x minus 1. So this is like a and a. Minus I plus I. This is minus bi plus bi. So I can use the same formula for the first two terms, brackets, and then for the last two brackets. I can use the formula twice. So it becomes x squared plus 1, first two here. Remember, there is an a. And then x minus 1 squared plus 1 also. Then I expand here, x squared minus 2x plus 1, and there is 1 here, becomes plus 2. When I multiply, I get all this. Remember, in the condition here, the given condition said the constant term should be 12. So this is 2 here. So to make it 12, I have to put here a 6. So a must be 6. Now 6 times this, minus 12, plus 18, minus 12, plus 12. There is an x here. Just check it, please. Linear and quadratic factors. Every polynomial function, we can factor it into linear and quadratic. A quadratic polynomial with no real zeros is called irreducible over the real numbers. So if we have x squared plus 9 or x squared plus 4, so we cannot factor it in real numbers. Remember, we can factor it in the complex. So we call them irreducible. So if we have this cube here, we can factor it as this, but we can continue if we need to use the complex numbers. This one, take x common, we have x power 4 minus 16. So x squared minus 4, x squared plus 4. This one we can do in the real numbers here, difference of two squares, this one in the complex. Let's factor the polynomial here, x power 7 minus 64x into linear factors. All the factors make it linear, like x minus something, x plus something. It's not that difficult. We can do it by normal factoring. If I take x here as a common factor, you know how to do that. Then we have x to the power 6 minus 64. So I can make it squared here, 8 squared, this one squared, use the difference between two squares. So x outside becomes x cubed plus 8, x cubed minus 8. This is easy. We have two formulas from the factoring. Sum of two cubes, difference of two cubes. You can continue and factor each one. Now we have big bracket here from the cube, x squared minus 2x plus 4. We need to use the quadratic formula because we cannot factor this. So if you use quadratic formula here, you get x equals 1 plus or minus square root of 3i. And then this is a difference between two cubes, x minus 2. Then you have another bracket, x squared plus 2x plus 4. Use the quadratic formula again, you get minus 1 plus or minus square root of 3i. Now the function given was, remember here, this is the function given, x power 7 minus 64x. You see the given here, x power 7 minus 64x. That means we have to have 7 linear factors, 1, 2, 3, 4, 5, 6, and 7. See, every c is a 0, then you can write x minus c is a factor. That's the whole answer. Nice idea here in this example, we need to solve the equation. See, solve it means find the x that will make it 0, as if we are saying find the zeros. Then after we finish, find the sum of the non-rational zeros. You know, some zeros are rational, some are irrational, some real, some complex. Every zero not rational, find the sum. So since here we cannot factor this easily, so what can we do? We use P and Q. So P and Q will be plus or minus 1, plus or minus 3, plus or minus 9. You can start with any number, do the synthetic. Let's make sure here the numbers are correct. 1 minus 5, 4, 3 and 9. Try 3. If you bring 3, 1 down here, 1 times 3, 3 minus 2, minus 6, minus 2, minus 6, minus, this is a 0. That means 3 is a 0. I told you many times, if you find a 0, try it again. Maybe it is repeated. So 1 comes down, 3, add, you get 1. And then here also you get 1. So that will be 0 again. 3 is a multiplicity 2. So I can take the quotient x squared plus x plus 1. On the next slide, I find a is 1, b is 1, c is 1. So use the quadratic formula, and these are the solutions. Now, this is rational. 3 is rational. This is complex. Maybe we have also irrationals in other questions for sure. Some of the irrationals, I take this complex and this complex. Okay. So if you add them here, you get -1. Now, these are the old exams questions. You can try yourself, practice on it. We have done some examples similar. List all the zeros and their multiplicities. So this is A and B. Nice questions to try. If 3i is a zero of this function, find the number of x-intercepts. Find a polynomial capital T of degree 5 that has integer coefficients, and the zeros are half, -1 of multiplicity 2, and -i. Also, the leading coefficient should be 4. Find the product of the complex zeros of this x power 5 plus x cubed plus 8x squared plus 8. So find all the zeros, take the complex, and then multiply them. Second part here, find the number of real zeros. How many real zeros? This is a nice question, really. We have x, polynomial x to the power 4 plus 4x squared minus 45. The zeros of this are, so you have to find the zeros and to know the type, and then you can choose, this is a multiple choice, A, B, C, D, E. Choose the correct answer. Question number 6, find a polynomial p of x of degree 3 that has integer coefficients and zeros half and 3 minus I. Find the lowest degree here of a polynomial with real coefficients having the zeros -6, 3 of multiplicity 2, 4 plus I, 7 minus I. So we need here only the degree, 9, 8, 7, 6, 5. If 2 is a zero of this function, huge function, x to the power 6, all this, if 2 is a zero, find the product of the non-rational, all the zeros that are not rational. So they can be irrational, they can be complex, they can be anything, but not rational. Find the product. Now these are the answers there, only the answers of the 8 questions. For complete solutions of these questions, 8 of them, please, you can see the video on complex zeros of polynomial functions, lecture 38. Thank you for watching. If you like the video, you can subscribe and share it with your friends. Just to remind you, this is lecture 38, the one before the last lecture. So lecture 39 will be the last lecture in the algebra course. Thank you guys for listening.